Hi, folks. Next, we're going to cover the history of the periodic table and how the periodic table is organized, why it looks the way it does. So, why make a periodic table at all? Well, scientists had started finding so many elements once we agreed that there were these chemical substances that could not be broken down by chemical means. Then scientists were on a hunt to find new elements all over the place. And soon they just found so many that they needed a way to organize them. So Dmitry Mendeleev was the first person to kind of successfully come up with a strategy for organizing the periodic table. He organized elements based off of similar chemical properties. He put elements with similar properties in the same column. And so he put them in order by increasing atomic mass. And when he did so, he noticed kind of every 8 or every 18 elements, certain repeating patterns in their chemical reactivity appeared. And whenever something recurs from time to time, we call that a periodic pattern, which is why we call this a periodic table. And so we call that idea that elements do have this repeating pattern of chemical and other properties, the periodic law. When you arrange elements in order of increasing atomic mass, elements with similar properties appear at regular intervals. Now, I said atomic mass because that's all that Mendeleev knew of when he created his periodic table. However, we now know that the periodic law is better described as when you arrange elements in order of increasing number of protons, so an increasing atomic number. That fits the periodic table better. But protons had not been discovered when Mendeleev came up with his periodic table. So as you can see here, we have lithium and potassium and rubidium kind of all grouped in a column together. And we have like chlorine and bromine grouped in a column together. And the extra powerful thing about what Mendeleev did is he left gaps where he thought new elements would be discovered along with their approximate masses. So here we've got silicon in a column, and here we have mystery element with a mass of about 72. And if you look at your own periodic table, you'll see that below silicon on the periodic table, there is germanium, which does have a mass of approximately 72. And so this was a really powerful tool because it had predictive properties that turned out to be correct. Now, Moseley was kind of the next person to make changes or improvements to the periodic table. And basically, after protons discovered, Moseley realized that that was the order in which elements needed to be placed on the periodic table. The elements fit the patterns of periodicity better when they are arranged by atomic number, the number of protons, not their mass. For example, if you compare the atomic mass versus the atomic number of iodine versus tellurium, you'll see that iodine belongs after tellurium on the periodic table because iodine is more similar to bromine and tellurium is more similar to selenium. But according to their mass, they would have originally been placed in the opposite order. Iodine actually has a smaller mass than tellurium. And this is the version of the periodic table that we use today. Elements are placed in order of atomic number. And here is the tellurium and iodine example that we were just talking about. So this is what the modern periodic table looks like. So we need some vocabulary so that we communicate well about the periodic table. So first of all, vertical columns. The vertical columns on the periodic table are called groups. And so there are 18 groups on the periodic table, and you just number them 1 through 18 from left to right. We do not assign groups to those extra 2 rows at the bottom of the periodic table, the lanthanide and actinide series. Elements that are in the same group have similar chemical and physical properties due to their electron configurations. They have the same number of valence electrons if they're in the same group as each other. There will be more about this later, about what valence electrons are and electron configurations. The horizontal rows also have a name. Those are called periods. And There are 7 of those, numbered 1 through 7 from top to bottom. And the periods relate to how many energy levels of electrons that an atom has. Physical and chemical properties change as you move across a period. So there are 3 main categories of elements. And the delineation between these 3 main categories is what I call the zigzag, or the staircase that runs between boron and aluminum down to between tellurium and polonium. Metals are to the left of this zigzag, with the exception of hydrogen. Hydrogen is not a metal, but it is located on the left side of the periodic table. As you can see, most elements are left of this zigzag, so most elements on the periodic table are metals. Nonmetals are to the right of the zigzag, so almost all of the nonmetals are shown here. The one that's missing is hydrogen. Hydrogen is a nonmetal. And then the 7 metalloids are on the zigzag. So boron, silicon, germanium, arsenic, antimony, tellurium, and polonium are the 7 metalloids. So what are the differences between these categories? Let's start with metals first. Metals are good conductors of heat and electricity. Most are solids at room temperature. Mercury is a common counterexample to that. Mercury is a liquid. Most are lustrous. Lustrous just means shiny. So your typical, the way appearance of a metal would be shiny. Most are malleable. That means when you hit them with a hammer, they don't shatter into fragments. They kind of stay stuck together and can be hammered into a thin sheet. Most are ductile. Ductile means that when you pull on it, it can be drawn into thin wires. Again, staying attached together, not fragmenting into lots of pieces. And most have a high tensile strength, so they resist breaking when you pull them. Nonmetals, not surprisingly, have kind of the opposite properties of metals. They are poor conductors of heat and electricity. Many are gases at room temperature. Solids are generally brittle. Nonmetals can be liquids or gases, but when they are solids, they tend to be brittle, so they'll fragment into pieces when hammered. Metalloids, not surprisingly, have properties kind of in between the properties of metals and nonmetals. So they're solid at room temperature. They tend to be semiconductors, so they kind of conduct electricity, or they conduct electricity under the right circumstances. They tend to be less malleable than metals, but less brittle than nonmetals, so kind of in between in terms of their malleability. And some, like this image here, are slightly lustrous. They're a little bit shiny, but not as shiny as a metal would be. So those are the general categories of elements: metals, nonmetals, and metalloids. But now we're going to drill down and look at special groups and their special names of regions on the periodic table. So everything in group 1 except for hydrogen is an alkali metal. So this is a special name for group 1 because these are special metals. We think of things as not reacting with water, but metals, when these alkali metals, when you put them in water, do react vigorously to the point where they will often ignite, as you can see in this image. Everything in the same group has a similar electron configuration, which we've not learned about yet, but go ahead and write this in your notes for later on in this module. We'll know about the electron configurations. Their electron configurations end with S1. That means that they're going to have 1 valence electron. That makes these metals extremely reactive. You just have to lose 1 electron for a full valence shell. They're like so close to having just the right electron configuration that they react extremely quickly. These metals are surprising. They're soft. You can cut them with a knife. They float on water because they are not dense. And they, as I've already said, they react with water. Please note again that hydrogen is not a metal. but it is extremely reactive. So we put it in group 1, but it is not an alkali metal. The second group we're going to talk about are the alkaline earth metals. This is what we call group 2. These metals are also reactive. You can see here that this magnesium is on fire, but not quite as reactive as those metals that were in group 1. So the electron configuration of these metals ends with S2, so they have 2 valence electrons. So they're reactive, but as I said, less reactive than group 1. These are harder and denser than group 1 metals, so they don't float, and they are more brittle. You wouldn't be able to cut them with a knife. One thing to note is that helium, which is over in group 18, also has an electron configuration that ends S2. But for small atoms, it has a full valence shell, so it's unreactive, so we leave it over there in group 18. We don't include helium in group 2. This is not in the paper copy of your notes, but just groups 13, 14, 15, and 16 don't have special names because there's quite a bit of variation in these groups. You tend to have nonmetals at the top of these groups and then metals at the bottom of these groups. So there's quite an assortment of different types of elements in this region of the periodic table. But these are all in the P block. There are no special names. Sometimes people will refer to these as like the boron group, the carbon group, the nitrogen group, just to kind of give it a name. But we have a mix of metals and metalloids and nonmetals here. Group 17 is the next group with a special name. We call these the halogens. And halogens have electron configurations that end with P5. These have 7 valence electrons, and that makes them extremely reactive again. They're not metals this time, like the group 1 alkali metals, but they are extremely reactive because they only have to gain 1 electron to have a full valence shell. And these are colorful elements. You can see from this picture here, fluorine and chlorine are kind of yellow and green gases. Bromine is an orange liquid, and iodine is a purple solid. In group 18, we have the noble gases, and their electron configurations end with P6. They have 8 valence electrons, and these are unreactive nonmetals. They have a full valence shell already. They don't need to react to change the number of valence electrons that they have. Note that helium is the exception to this electron configuration rule. Its electron configuration ends S2, even though it has a full valence shell. So it's an unreactive nonmetal. We put it in group 18. The next special name I want you to know about the periodic table are these tall groups, groups 1, 2, and 13 through 18. We call these the main group elements. Groups 1 and 2 have a special name. We call that the S block, including helium. We do include helium in terms of the S block over here. And groups 13 through 18 are the P block. That excludes helium, so we don't count helium in the P block. So this is the P block, this is the S block, and we count helium over here. And the S and P blocks together are the main group elements. These elements behave differently to the transition metals, which are in the dip of the periodic table here, as well as the lanthanide and actinide series that we see down here. So I already hinted at this, but elements in the dip of the periodic table are called transition metals. So those are groups 3 through 12. We can also call this region of the periodic table the D block. And these metals are less reactive than groups 1 and 2. And these are your typical metals that you expect to see here. So iron, copper, zinc, silver, gold, platinum, metals that this contains most of the metals that you've heard of. Another region of the periodic table that we need to cover are the lanthanide and actinide metals. The F block is placed below the other blocks on the periodic table so that the periodic table can fit on one page. Otherwise, the periodic table ends up looking like this one here. So the lanthanide and the actinide series are typically written below the other parts of the periodic table. We do call those two together the F block, but it's important to realize that they don't have their own periods. There are just 7 periods on the periodic table. 1, 2, 3, 4, 5, 6, 7. And the lanthanides belong here in period 6, and the actinides belong here in period 7. I hope this helped.